Lesson number 11, demo. In this class, we calculate and interpret second derivatives. There are 2 demos and 2 activities today. Number 1, for f of x equals x to the 4th minus x, find f of 2, f prime of 2, f double prime of 2, f triple prime of 2, and then f with a little 4 in parentheses of 2. Okay, let's start with the familiar pieces of this problem. So we know how to find f of 2, right? We just plug 2 in to the original function, so 2 to the 4th minus 2. That's 14. And f prime of 2, I can do that no problem. That's old. So f prime of x, using our power rule, the 4 comes down, copy the x, subtract 1 from the power. The derivative of minus x is minus 1, the invisible minus 1 sitting in front of that x. And so I can use that to find f prime of 2, just plugging 2 into this new formula we've created. 4 times 2 cubed minus 1. 4 times 8 is 32, minus 1 is 31. But f double prime of 2, this is new for us. Well, f double prime would seem to indicate the second derivative, or said another way, the derivative of the derivative. So if I just think of this as being my starting function, I could certainly take its derivative, and a good name for that would be the second derivative of f. So f double prime is the derivative of the derivative. The derivative of 4x cubed minus 1, again, that's our power rule. 3 comes down, 12x squared, the minus 1 becomes a 0. So there you go, that's our first second derivative. It's the derivative of the derivative. And of course, we could plug any number we want in here. So in particular, plugging 2 in, 12 times 2 squared, 48. Okay, well, that was so much fun. Let's do it again. F triple prime, 1, 2, 3, oops, one more. 1, 2, 3 of x. So that would be the derivative of f double prime, the derivative of the second derivative. The derivative of 12x squared, 2 comes down, 24x to the first. I won't write the 1. And then we can plug in 2 for x. So 24 times 2 also happens to be 48. That's a coincidence. Okay, and then the last one, well, I mean, like this is certainly brand new notation here. This f with a 4th, like it kind of looks like a 4th power, but the parentheses actually indicate it is the 4th derivative. And the reason we choose to write that new notation is that writing 4 primes is awkward, and reading 4 primes might be difficult and error prone. So if you see a number up there on a function, like the f there, but that number is in parentheses, it is not a power, it is the order of the derivative. So this means the 4th derivative, which means the derivative of the 3rd derivative. We saw down there in green, the 3rd derivative is 24x. So its derivative, one more derivative, is just 24. And then we can plug in 2. And of course, this function is always 24, so it doesn't matter that we plugged in 2 versus any other number. And then the 5th derivative, which isn't asked for here, but that would be 0. And in fact, every derivative after the 4th derivative is going to be 0. So number 2 says, here's how we can write a second derivative using Liveness notation. So we know that f double prime now means the derivative, that's this symbol, means take the derivative of whatever you see next, of the derivative of f of x. And so, so hopefully that's clear that that's the second derivative. But let's go ahead and combine some of these things. I'm going to treat this and this like a fraction. And if I treat them like fractions, which they aren't, they represent an operation. They mean take a derivative of. But if I treat them like fractions, then I can look at this as being fraction multiplication. And to multiply fractions, I just multiply straight across. So if I'm being very naive, I would say, okay, I've got d getting squared, and then I've got dx, that's one symbol, getting squared, and then I'll copy the brackets f of x. So it looks kind of wonky, but we're just treating it like fraction multiplication. And then finally, we're not going to write the parentheses. We're just going to write d squared, and then even though dx is a single symbol, we're going to not write the parentheses. You don't want to look at that and think it's x squared with a single d in the front. No, it's a dx is one symbol, even though it's 2 letters. And then we'll copy your f of x. So that's the Leibniz way to say second derivative. And for example, if we go down to number 3, we see a lot of different ways to write the fourth derivative. So we've already seen this 4 here in parentheses. And we can write it like there too, not just f to the fourth with parentheses, but y to the fourth, right? F and y are the same thing. And then the Leibniz version, hopefully we can convince ourselves this is just that, right? But with 4s instead of 2s. So that's reasonable. And then finally, another Leibniz version is this, where all we've done is replaced the f of x that we had here with a y, and then we put it on top because that's, after all, that's where it is, right? This f of x is definitely not on the bottom of the fraction, it's on the top. And a lot of students balk at this Leibniz version of things right here because it sure looks like we're putting the 4 in 2 different places. On the top, the 4 is, it looks like it's on the d, and on the bottom, the 4, it looks like it's on the x. But I mean, it makes sense, right? Like we just multiplied things out, and that's exactly where the 2's ended up. So even though it looks, you know, like sort of asymmetric, that is the way that we write it. Okay, number 4. We now introduce a concept known as concavity. You might have seen this in a pre-calculus class. Let's write the intervals of concavity for these 3 graphs using interval notation and analyze f prime and f double prime on those intervals. We'll be sure to exclude our endpoints on all intervals. Okay, let's take a look at this first graph on the top left. I'm going to pick 5 points on this graph, 1, 2, 3, 4, and 5. And I'm going to estimate the derivative at these 5 points. And we know that the derivative is the slope of the tangent line, so it sure feels like we should be drawing some tangent lines in here. So that one is steep downhill. That one's still downhill, but not quite as steep. And I'm missing my curve here. Let's try this again. Steep downhill, downhill, but not as steep. This one here, and then now we start to get to the uphill ones, and then very steep uphill there. And so if I could just ballpark the slopes of these tangent lines, I would say that maybe this one is negative, I don't know, 4. Maybe this one here is like a negative 2 or 3, which still looks pretty steep. Let's call that a negative 3. Down here we've got a 0. I guess by symmetry, I should call that positive 3. It's the partner of the negative 3. And then we'll call this one positive 4. And we know that the slopes of the tangent lines are all f primes. So like these green numbers are the values of f prime. And if I just look at this collection of values of f prime, just this list of 5 green numbers, the question is this list of 5 green numbers decreasing or increasing or some combination of the two as we go left to right? So we go negative 4, negative 3, 0, 3, 4. And hopefully we agree that is an increasing list of numbers. And so we are going to say that anytime the slopes form an increasing list of numbers, we call the function concave up. I'll say it again. If the slopes form an increasing list of numbers, we call the function concave up. You don't need to write that. We're going to have a better way to think about this pretty soon, but that's essentially our definition. And so this function right here is concave up, and we're going to say the interval where it's concave up, and we're talking about the x's here. And this guy is concave up for every single x. And so the way that we write that with interval notation is minus infinity to infinity. That collection of derivative numbers is increasing the entire time. So the function itself is concave up the entire time. We're giving x values. And it's not concave down at all. That's what the CD stands for. We'll see some concave down ones coming up. And let's go ahead and analyze what's happening here with f prime. So we said that on this entire interval, f prime is forming an increasing collection of numbers. So f prime is increasing on minus infinity to infinity. And I guess I can actually cross off, like it's not concave down anywhere. We're not analyzing f double prime where it's concave down, and we're not analyzing f double prime where it's concave down. So the last thing here is to analyze f double prime where it's concave up, which is everywhere. All right, so here's the trickiest part of this. We know that the values of f prime formed an increasing list of numbers. And here's an old fact for us, is that anytime a function is increasing, its derivative is positive. Anytime a function is increasing, its derivative is positive. I'll call your attention over here to this graph on the far right. And this function is increasing the entire time. And as a result, the derivatives of this function are always positive. So that is an uphill tangent line. That's an uphill tangent line. That's an uphill tangent line. Every single tangent line is positive because that original function is increasing. I'll say it one more time. If a function is increasing, then its derivative is positive. Okay, take a look right here. We have a function which is increasing. That function is not f. The f function, after all, is decreasing for a bit and then increasing. So that is not the function I'm talking about when I say we have an increasing function. Our increasing function is f prime. And as we said, if a function is increasing, its derivative is positive. And my function that's increasing is f prime, so its derivative must be positive. The derivative of f prime must be positive. And what's a good name for the derivative of f double prime? Well, it's what's a good name for the derivative of f prime? It's f double prime. And so because f prime's derivative must be positive the whole time, then f double prime is positive the whole time. So it's kind of a long way to go here, but our general conclusion is that if you've got a function that's concave up, like this picture here, then its second derivative is positive. F double prime and concave up are going to be synonymous for us now. Okay, I know that that's tricky, that connection between the f prime increasing and the f double prime being positive. We'll try it again on the middle graph here. So again, I am going to plot some points. 1, 2, 3, 4, and 5, and then draw 5 tangent lines. And estimate some slopes. So maybe in this case, it's, I don't know, a slope of 5, and let's call this one a slope of 2, 0, -2, -5. In this case, the slopes form a list of numbers that is which one, increasing or decreasing. So in this case, 5, 2, 0, -2, -5 is a decreasing list of numbers. And whenever we have the slopes of tangent lines forming a decreasing list, we say that the function is concave down. And this function is concave down everywhere. And so I'm actually going to cross off the concave up column. Not worried about that for this one. Okay, let's take a look at this next piece here. We want to know if f prime is increasing or decreasing. Well, as you read these numbers left to right, hopefully you agree that is a decreasing collection of numbers. So f prime is decreasing the entire time. And now I'll say a sentence from our past. If a function is decreasing, then its derivative is negative. Again, if a function is decreasing, its derivative is negative. Well, I have a function that's decreasing. It's f prime. That is a decreasing function. So its derivative must be negative. The derivative of f prime must be negative. And what's a good name for the derivative of f prime? Well, it's f double prime. And so f double prime must be negative the whole time, -infinity to infinity. And so again, we're now making another connection here. If a function is concave down, then its second derivative is negative, and we're going to have those two being synonymous with each other. Okay, last graph is the most complicated one. Let's take a look at some slopes of tangent lines. Again, I'll put 5 points here. Let's go 1, 2, 3, 4, and 5. And we're going to draw our 5 tangent lines. So pretty steep uphill. Not quite a steep uphill. Not quite a steep uphill. Steeper uphill. Very steep uphill. Okay, so let's call this first one here. Maybe this is a 3, and I'll exaggerate and call that a 2. I don't think it's a 2. I think it's closer to 1. And then we're back to 2, and then we're back to 3. So is this collection of 5 numbers, as you read them left to right, does it form an increasing collection, a decreasing collection, or some mixture of the two? And hopefully we see this as a mixture, right? Like in the beginning, 3, 2, 1 is decreasing. But then at the end, 1, 2, 3 is increasing. And so actually this is one where it's partially concave up and partially concave down. So as we said, if a function is, if a collection of derivative numbers is decreasing, like we are here from 3 to 2 to 1, then the function is concave down. And so again, concavity is always given for the x's. So this function is concave down from the beginning of time up until 0, -infinity up until 0, we have a decreasing collection of slope numbers, and so that function is concave down. And then from 0 onwards to the right, the function is concave up because you have an increasing collection of slope numbers. Okay, so let's circle the right words here. I'll start from the 0 to infinity side. So f prime, that list of green numbers, is this an increasing or decreasing list? It's increasing. So f prime is increasing on this interval here, 0 to infinity. And because f prime is increasing, its derivative is positive. That means that f double prime is positive, again, on the interval 0 to infinity for the x's. And then on the other side, from minus infinity to 0, if I'm just looking at this collection of slopes, 3, 2, 1, that is a decreasing collection. And because f prime is decreasing, its derivative must be negative, and its derivative is called f double prime. Okay, so we're going to have lots of stuff summarized on the next page, but for right now, I would like a graphical way to just look at a graph, look at a picture, and decide where the function is concave up and where the function is concave down. So here we go. Number 5, if a graph can hold water like a cup, then the function is concave up. If the graph can hold water like a cup, then the function is concave up. So take a look at this graph right here at the top left. That sure looks like a cup. It could hold water. If you had water coming in here, it would just stay right in there. And so that graph is concave up the entire time. So cup, concave up. If a graph looks like a frown, then the function is concave down. You see what I did there? I'm clever. So take a look at this frown right here, very sad, sad parabola. And if you were to try to put water in here, it would just dribble right back out. It is definitely not a cup, it is a frown. And so that graph is concave down the entire time. Okay, what about this one that's a mixture? All right, so let's take a look here. In the beginning part, so here to here is definitely not a cup, right? Like if you were to put water in, it would just fall right out. So it is the beginning of a frown. It's part of a frown, isn't it? Like if the behavior were to continue, like if this trend were to continue, you get the complete frown. So you only have part of a frown, but for the part that's a frown, the graph is concave down. And it stops being frown-like right around the origin there. And when you pass the origin, you get this. Now, it's not a cup, right? Because like if you were to put water in here, I guess you could argue that it would just dribble off to the side. So it's not holding water, but that's just because the cup hasn't been completed. If I were to let this trend continue, I'd get the rest of my cup and then the water could sit there and stay. And so you kind of have to use your imagination with these frowns and cups. Typically, you only have part of a frown or part of a cup. Okay, on the next page is our summary. And number 1, or the first sentence here, if f prime is positive, then f is. Our choices are increasing and decreasing. Which word goes in the blank there? Maybe pause the video, give yourself a moment to think about it. If f prime is positive, then f is increasing. So this is an old statement, nothing new here. And if f prime is negative, then f is decreasing. But then the new stuff is in the next 2 sentences. If f double prime is positive, then f prime is an increasing function. And therefore f is called concave up. And again, I'd really like us to have this, this connection between the first thing here and the last thing. F double prime positive means f is concave up. Those are one and the same. And if f double prime is negative, that means f prime is a decreasing function. And f is therefore concave down. And again, I want the first and last connection to be very strong. If f double prime is negative, then f itself is concave down. Okay, number 7 is a definition. A point on a curve, y equals f of x, is called a point of inflection or an inflection point for the curve if the concavity of the curve changes at that point. To find points of inflection, find where the second derivative is 0 or undefined and perform a sign test on the second derivative. Let's give it a shot. So looking at this graph right here, this is this left-hand one. The graph is concave up here because that looks like the beginnings of a cup, and then it becomes frowny, so concave down. And right there, that one magical spot is called x0 here, is called an inflection point or a point of inflection. Same deal here. I've got part of a frown, so concave down for this interval of x's. And then I've got the beginnings of a cup, so concave up for this interval of x's. And the spot where things change is called a point of inflection or an inflection point. Okay, so number 8 says let's find the quote intervals of concavity and inflection points for this function right here. Okay, so clearly, and concavity has to do with the second derivative, so let's take two derivatives of this function. F prime of x equals 3x squared minus 8x minus 16. You could set that equal to 0 if you wanted to find where the graph was flat, but that is not what we're after here. So the only point in getting f prime is actually to get f double prime. So we take our second derivative here, 6x minus 8. And I'm interested in knowing where the second derivative is positive and negative. Because where the second derivative is positive, I know my function f is concave up. And when the second derivative is negative, f is concave down. And I'm looking for the place where that behavior changes. And that's where the second derivative is identically equal to 0. So we set the second derivative equal to 0 and solve for x. And I get x equals 4/3 as a possible point of inflection. And so to actually figure out if it really is a point of inflection, we're doing a sign test. So here we go. You put 4/3 on your number line. And you always label the number line with the function that this number came from. So 4/3 came directly out of the second derivative. So we are doing a sign test on f double prime. Okay, so let's plug in. We're going to pick any number out here to the right of 4/3 and plug into the original f double prime. For example, I'll pick 100 for my x. If I pick 100 and put it right here for x, I get 600 minus 8, that's 592. All I care about is that it's positive. Don't so much care about the 592, just that it's positive. And then you can pick a number here less than 4/3. You could pick 0. I'll pick negative 100. So negative 100 for x, that's negative 600 minus 8 more. Not sure what that is, but it's definitely negative. Okay, I was just kidding. It's negative 608. I knew what it was, but the point is, we don't care what it is other than the fact that it's positive or negative. Okay, and so then in terms of identifying the intervals of concavity, I think we've got our answer here. We know that f is concave up whenever the second derivative is positive, which is to the right of 4/3. 4/3, comma, infinity. We're just always going to exclude the endpoints here. We'll say the function is not concave up or concave down at 4/3. So where is it concave down? Concave down where the second derivative is negative, which was up until 4/3. And so we'll put minus infinity there. And then finally, our point of inflection. Point of inflection is the place where the concavity changes. It's at x equals 4/3 and then comma, and then, I mean, technically a point of inflection has two numbers, right? It's a point. So I guess to find the y coordinate, I would plug 4/3 into the original function. So I just did that on my calculator and got roughly negative 14.07 for the y. You can write that as a fraction if you want. So that's our point of inflection. It's a place where the concavity changes. I will highlight that you only have a point of inflection if the concavity changes. This 4/3 coming out right here is not automatically a point of inflection. It only was a point of inflection because of this sign change. If they had both been positive, then 4/3 would not be a point of inflection because the function would have been concave up from a positive here and then concave up from a positive here. And a point of inflection is a place where the concavity changes from concave up to down or from concave down to up. Okay, so as I mentioned, there are 2 demos and 2 activities. I'll make videos for all of these things, but go ahead and start demo 1 here start activity 1 now. And then once you finish that, come back to check out demo number 2.